we're going to have a session on landslide risk assessment and decision making, how is good link and what type of information would be required from a landslide risk assessment to make the proper decisions. That's also related to the scale at which we do that. We're going to look at a number of examples this morning of how risk information, landslide risk information is used for decision making. We go through a certain order as well in the presentation. So we start with the presentation dealing more with inventory and susceptibility mapping and the problems involved in getting landslide inventories. Then we have the presentation that links landslide susceptibility and hazard maps to spatial planning. And the third presentation will focus on the use of landslide information in community-based design of risk reduction measures. We had a fourth presentation scheduled, but unfortunately that's from Cynthia Linero Molina, a senior geotechnical engineer from the World Bank. She was going to present some of the work she did in Medellin, Colombia, but unfortunately she couldn't make it. So depending on the time, if there's still time, I will do a wrap-up part. But we see how we go. So the first presentation is from Dr. Suleimani Diop. He's an engineering geologist from the Engineering Geoscience Unit of the Council of Geoscience. He did his PhD in Japan, and he's totally fluently speaks Japanese. But I guess I can do it in English.
Thank you, Chef. I'm happy to see some faces. Before I start, is there anyone from government organization in South Africa? No? One? Okay. One, yes. So I'm very happy to see you guys, and I've been talking a lot to you just now. To start this presentation, I would like first to pay some tribute to some of my colleagues, first from DST and DMR who actually agreed to give us some fund for this research. DST, Department of Science and Technology, and Department of Mineral Resources. Actually, we belong to those two departments in terms of our statutory obligation. I would also like to thank Rebecca, who's done a lot. Actually, she was supposed to be here to make this presentation. I also like to thank Colin and Goodman, who are from the engineering unit, Goodman did the work in Limpopo, while Colin did part of the work in Western Cape. Rebecca was busy on KZN. I mean, for those who are not very familiar with South Africa, because we take it as granted that everybody knows about South Africa. So I'll be talking about some of the provinces. Okay, here is the Limpopo. We'll talk about it a lot. Here is KZN, KwaZulu-Natal, Western Cape right there. You see Cape Town is a tiny place in there. So you see South Africa is quite big. And then this map shows actually elevation around South Africa. You'll see like the most elevated area is about here and here. That's why we focus on Limpopo, KZN, and then Western Cape for now. We have a project on doing some work in Free State and then Eastern Cape and Northwest. But for now, we just focus on those three main areas. I just want to share with you a couple of slides of some events that happened here in South Africa recently. I mean from 2009 to now. Here you have a picture in Limpopo where you see this huge mass of land was just taken away down the road during the 2000 event. And 2000 was like a combination of heavy rainfall, flooding, and then a number of landslides that occurred around the area. And during this type of survey, and that's one of the limitations we have in South Africa, access to some private owned land is a main concern. Sometimes you just cannot have access to the land. Someone will tell you it is a private thing, you cannot get in. And if you know, like most of South Africa is made of farms. So sometimes it's very hard to get to that area to get information. So we need to do some politics. I mean, like local politics, sorry. So as you can see here is a chief in one of those Limpopo area. So we had to go to see the chief, talk to him, bring some small presents, so then we can grant us access to some area. And here we talk to some ladies in the area who know the history of the area, so then to get some eyewitness events, so then they tell us this area had this type of landslide at this type of period. So that's how we collected some of the data. Sorry. And here is another big paleo landslide that happened in Lake Fundutsi. If you from South Africa, you may hear from this huge mass of rock just went down and then created what we call here like the Fundutsi Lake, because it was a river, Mutali River, that this huge paleo sinkhole, like it's quite big. If you see like this huge mass just went down and then blocked the river, ending up creating a lake. But you don't want to use that explanation to the chief I just showed you, because he doesn't want to hear about that, because he's got his own explanation about how the lake forms, and it's nothing to do with landslide and geology. So we agree not to mention it in front of him. And here you see this type of event can happen anytime, like you driving and some huge block of rock can just fall over you. This is one of the main problems in South Africa, like the design of road cutting and stuff. They don't take into consideration this type of thing, and it's very, very common in South Africa. And here are some other here. I like this one because this guy was the guy who designed this road. He's great actually, because look at this huge block with this subvertical jointing. This is happening to fall sometimes somewhere with the condition are met. So this is the type of thing we can explain. This toppling can happen anytime. This is another example in here we are in Western Cape, so not very far from here. Another huge mass of ground just went down. This is the railroad here, and then some housing around there. And this is an example of debris slide. To give you an example of the size, look at the car right there. So this whole mass went down. Another example, if you most likely have heard about the Chapman's Peak Drive. It's beautiful scenery. You can see the sea and everything, but you can also have some accident happening where some huge block can just drop in front of, like this car, for example, was smashed 1994. Since 1998 up to 1988 up to now, we have a lot of events in Chapman's Peak. I will just summarize it just now. Here is, you talked last time during your Ignite about these new landslides. Was it Uganda recently? Yes. So these will remind you, look at, this is beautiful actually. I mean, it's really beautiful. I mean, if you are a geologist and stuff. Those white dots are not cows, they are houses. So, and as you can see, people live in here, and you see this deeply incised gully. This is a disaster waiting to happen. As we said, are we proactive, or are we just reacting to the events? So this is the type of thing we need local authorities to know about, so then this thing would not happen. I mean, like, normally people should not live in this type of environment. But nobody, I mean, we're trying to say it, but is there anyone to listen to us? And finally, we all like having this nice view of a Table Mountain, the sea, and stuff like that, but this guy has got block of rock as a view. This is not what we like. This happened in Johannesburg, Bruma. This was in 1994, I think. So landslide is a real thing in South Africa. We don't talk about it, you don't hear a lot about it in the news, but it does happen. So today we have approximately 2,376 events we recorded from the Council for Geoscience. But it's very limited extent, like we've just done it for 2 or 3 provinces, and we have 9 provinces. Most of the provinces have not been touched. Even those 3 provinces I'm talking about, they have not all been covered. This is just a small, tiny summary of what we've done so far. And for example, now here in terms of casualties, okay, 6 people died in 1987 in KwaZulu-Natal during the Stanley debris flow. This one, maybe most people will notice this on 101 people dead in Limpopo. People will tell me it's not all about landslide, obviously, because it's a combination of things. That was like heavy rain, flooding, and a lot of landslide happened during that time. So when we combine everything from the Limpopo Provincial Disaster Management Center, it came up to 101 people dead. 17 people died during the Maize Street slime dam collapse, very famous all over the world, people talking about it. It's a slime dam, but still a mass wasting event. And 5 people dead in Western Cape between 1988 and 2000 from the Chapman Peak Drive, mostly from rockfall. Now, here, I like this because someone mentioned it during the Ignite session. These are predictable surprises. We always act like it's a surprise, but it's predictable. I've shown you just a picture. Some of those things will happen. They are predictable. What are we doing about it? Are we waiting until it happens so then we rush to the Council for Geoscience, here is the money, do something? We're asking the money now. Guys, from the government, I want the money now, not after it happened. So financially speaking, in the Southern Africa, so far, in 1989, Page Green has estimated the cost due to landslide to 20 million. If we add inflation and everything, it comes to 163 million US dollar, not rand, in terms of cost to now. So we know approximately how much it costs us so far, landslide. What I want to highlight here is this 845 billion rand project that the government has over the next 3 years to invest in infrastructure. How much of this are we going to lose due to landslide or other geohazards? Do we have any idea about it? I don't think so. And is it worth it, like spending all this money without having a proper disaster management plan in terms of what are we going to lose? We know what we're losing now. How much are we going to lose? How much can we allow ourselves to spend without having a proper disaster management plan? I want the decider to think about it, and I will come and see you later, or we can talk and then you can see how much can you give us to do a proper investigation. And I hope also the World Bank guy will help us on that matter. So there is the problem we have in terms of landslide in South Africa. And CGS, the Council for Geoscience, have initiated a project recently to go around, see all the landslide events, have an inventorization and try to propose a susceptibility map into the country. And I always show this to politicians or decision makers. Said, you see, we've even been awarded the World Center of Excellence because it's a fancy word. I love it. So then they can say, okay, you are a World Center of Excellence, so here's the money. But it doesn't happen. So I hope it will. I always try to impress them with this, but it seems they're not buying. And someone mentioned yesterday during one session that maybe we should be involved in politics, the scientists, we should be involved in politics because obviously nobody is listening to us. But I just guess we have to speak their language. I mean, we are speaking 2 different languages. I don't mean English, Afrikaans, or Zulu. I mean, like, we don't understand each other. Obviously, we put a lot of colors and nice pictures of Excel sheet and stuff like that. And they don't want to see it. They want to see something concrete. Maybe we'll work on it. But I hope some of them here will report back and then come and see us. Okay, this project is basically intended to meet the growing demand of local authorities in terms of putting forward a reliable predictive system, warning of the likelihood of landslide occurrence in the country. We hope through that what we are doing, some like the community, the money they invest in infrastructure and stuff is not going to waste, that they will take into consideration our recommendation in terms of designing and then implementing some infrastructure investment. Okay, here is now how we've done it. We have 3 phases. I have to go a little bit faster. I think I'm a little bit late. Okay, first we compile all the landslide events that occurred in the country. We have inventory map of how many landslides have occurred, and then we'll use this nice suggestion from Ermini that actually the past is key to the future. if we know what happened in the past in some area on some condition, so if those conditions repeat themselves in the future in a similar environment, then we can expect that landslide will occur. So that's what we're using for this. The second phase will be to use a modeling technique to put all together and then in an understandable way. So we use the bivariate statistical landslide susceptibility modeling, and we added the analytical hierarchy process to make sense of what we gathered and then have some weighting, some type of thing that can make sense to the politician or the decision maker so that he can take some decision. I mentioned the second method, but we've used it just to have two methodologies that when we have the two maps and then it correlates well, so then we said, okay, we are on the right track. But I will not really develop on this one. We just will go through this first methodology, and then I will show you the results of that. So it's gone. Okay, the phase 3 now is a quality control. So we've done our inventorization, we've done the susceptibility mapping. How good is the map? So we'll have some landslide events outside of our modeling that were not taken into consideration during the modeling, and then see when we fit them into the model if they are reliable or not. And here is the causal factor, because landslide just doesn't happen like this. Landslide happen when the triggering mechanism is in place, when some conditions are met. So here we send a questionnaire out there to professionals, the politicians, municipal authorities, telling them what do you think are the main cause of landslide. And then we come up with those 9 parameters: slope angle, how steep is your slope, the relief, the rainfall, because it's one of the main parameters, the geology, obviously, being a geologist and all, seismicity. I know people really like seismology in South Africa, and they'll be happy to see it. So maybe that's one of the reasons we put it there. You never know. Okay, the morphology of the terrain, dolerite contact zone. This may be surprising to many people, but in South Africa, it's quite a very important parameters, because we do have a lot of dolerite sill and then contact zone in KZN and the Karoo area mostly. Lineament, and finally human-induced effect. I showed you some of the picture like road cut, like fire and stuff like that. So they are human-induced parameters. No, what is this now? It's not supposed to be like this. Anyway, that's a formula that went wrong. Anyway, so we use those causal factors to combine them into some weighting or some ranking values. And then we use, for example, here is supposed to be the landslide density that we calculate for each subclass. This is subclass. So it's the number of landslide in one subclass over the size of that subclass. Let's say an example, if we take, let's say shale, geology of shale light. How many landslides do we have in a shale, let's say, divided over the size of that shale is occupying in that area? So we end up with a landslide density. So now those are ranked into like 3 categories, 1, 2, and 3, 1 being the lowest susceptibility and 3 being the highest susceptibility. And we do it systematically for all subclass and then causal factor. Here is the inventory map. You will see we just focus for now from these 3 area, Limpopo, KZN, and part of Western Cape. We didn't touch on, actually it would be more, we put more weight now when I'm talking, if we have touched Cape Town. So people will say, oh yeah, we have something in Cape Town. But it's coming anyway. 2,367 events distributed as you see. That's, and just to tell you about this whole method, how it's gone, because I was asked by Trish to insist on what methodology we've used. I'll just give you 2 examples, slope angle and then relative relief classes. Basically what we do for slope angle, we divide it into classes. Here we have 4 classes in terms of 0 to 6 degrees, and then you will have a landslide point count, how many landslides have occurred in an area, it's a flattish area, 325 event occur, the size of the area, the density, and then the ranking value. 1 is very low susceptibility. And we do that for all classes. For example, here for area over 18. And then the choice of these classes is not just random, because in South Africa, for all geotechnical investigation, if you are in an area over 18 degrees, it's not deemed suitable for settlement. So that's why we choose 18 degrees as the highest value. So anything over 18 degrees for the geotechnical mapping is deemed unnecessary. But here we have 633 events in this 18 degrees, and then for a ranking value of 3, which is a high susceptibility to landslide occurrence. The same apply to relative relief also, where we have 7 classes and different type of point count, and obviously the ranking. That's how we do it, and we do it for each of those 9 causal factors, and then we end up having ranking values. And here, something is wrong. But anyway, so here are the causal factors maps. Each of them we compute, as I showed you just now, having classes, and then we plot them for a national scale, and then you have causal factor. Here is for slope angle. You see where it's high, it's red, and where it's low, it's green. So we do it for all of the causal factor for geology, lithology. Just going quickly, that this is terrain morphology. This is the relative relief, and you see like it's quite a lot of high like susceptibilities. Cape Town, you over there, you see you are red, so you need to come and see us. And here we have rainfall, mean rainfall, and then you will notice, because I have to insist on this also, like the rainfall area, like we see around this Limpopo, Mpumalanga going down here, and Cape Town right there also. So the mean rainfall is quite like where you have dark blue is where we have estimated have high rainfall. Obviously, we will not have much of rainfall in the whole Karoo area. And then here we have now the dolerite contact zone. As I was mentioning to you, this is quite an important factor. You see how intense the dolerite contact zone is about in the Karoo, mostly Karoo, KZN, and then. So it plays a determinant factor in terms of landslides occurrence in this country. And seismology, seismicity, we have some nodes, but when you go around in this area, some of seismology guys out here is mostly induced, mining induced, but around here it's natural maybe. But here it's mostly mining induced seismicity. And finally, we have the lineament that can be anything from structural event like fracturing, faulting, bedding plane, and so on. So now here is how it's done. So we've selected these 2 methodologies in terms of analytical hierarchy process, the SATI method and then the CCI method, which is the Canadian Conservation Institute, whereby you compare a pair of causal factors, A to B. You said, okay, how important is A compared to B? So if A is extremely important compared to B, let's say you say rainfall is more important than dolerite contact zone. How is it like? Is it like extremely more important or not? If it's more important, it's 9, from 9 to 1, which is equally important. When the 2 parameters are equally important, you give it 1 to -1 according to this system. And then if it's highly important, it's 9. Then it goes from 1 to 9. And then the reverse is like if A is extremely more important than B, which is a 9, that means B is extremely less important than A, then you give it a -9. So for this study, we will use the CCI scale. And then we do it for all, remember we had 9 causal factors. For example, here I'll just give you for slope angle versus the remaining 7 And then we ask decision makers, there can be a specialist of landslide, that can be local authorities, that can be anyone we deem has some expertise in landslide, and we ask them the question, how is slope angle compared to relative relief? And then the 3 of them will answer, we have the sum, and then we have the mean value. But it doesn't mean we'll automatically consider that mean value. Sometimes you have to reject it based on some technicalities I will not go through, but people who are in landslide know. But sometimes it's nice to know, like, people agree. For example, here they all say slope angle is 7 compared to rainfall, and then the average is 7. Sometimes also here nice agreement. So we have some calculation to do, and sometimes we have to put some weighting in those factors. So that's how we do it for each causal factor compared to the remaining 7, and then we go through the whole thing, and that we end up having something like the weight value for each parameter now. Now here you will notice that in this table, slope angle and relative relief have the highest weight value. That means in South Africa, slope angle and relative relief played a bigger role in landslide occurrence. So, and then you will notice that when you sum all of these, it should add up to 1, which is 100%. It makes sense. And then this is like, when we use this factor now, we go and calculate the landslide susceptibility coefficient through this formula. It's basically you use that parameter with his weights, and you add up all of them, you end up with this landslide susceptibility coefficient. That's like this formula you apply to each cell in the whole map. So you end up having the susceptibility map of the whole country. And here is the national landslide susceptibility map of South Africa. Green being low susceptibility and red being high susceptibility. Cape Town, you're red. We need the money. Okay. And then you will see now like the susceptibility mapping, like most of the country actually is on green. Obviously, into the Karoo, you don't expect any landslide. It's a flat area, and then so it just makes sense. And then you will see now Limpopo, Mpumalanga coming down to KZN, okay, Eastern Cape, coming down to Western Cape. And then you see some in Gauteng, because Gauteng we do have also some high area. And then we also have the other version of it. That's when we plot all our events actually, and then see how good it correlates. You have to bear with me, like some areas we've not done any actually ground truthing. There is no ground truthing, there is no inventorization in that area, but based on that theory I told you, the past hold the key to the future, we were able to have this. And now that was a national one. This is at a provincial level. This is for KZN, which we completed. KZN is done. And this is for Limpopo, which is also done and completed. Basically, that was it. Now, this is the last part of the investigation, is verifying. So we've done it, and then we have some extra 65 verification sites where we know landslide occurred because we've seen it, we measured it. And then now we took with those 65, and then we plotted into our map to see how good our map was. So it ended up, because if it's a landslide, if it's occurred, they all should fall within high susceptibility. So we end up having 2 in the low susceptibility, which doesn't make sense, but anyway. And then 11 in the moderate susceptibility, which represents 17%, but bear with me, like 80% of our points actually went right into the high susceptibility. And if you add up the high susceptibility and the moderate susceptibility, you end up with a 97% accuracy somehow. I think we are doing a good job. Finally, conclusion. So we need just to mention in this that we do have past and present landslide events, but it doesn't mean that we went like the whole area, like those 2,360 something I mentioned are not the whole landslide event in South Africa. It's, I mean, far beyond, more than that. So what we've done is just a small, tiny portion, and then why, some people will ask me why you didn't do everything else, because we don't have the money, because we're asking for the money and it's not coming, and I hope from this one, you guys will be running to me and giving me the money. Okay, and then, now the establishment of the full special record of their complete characterization is necessary as community and formal urban growth expand into area prone to form of landslide, just like I show you in the KZ, and you see those people living in that hilly area. So we need to do the full identification, the full implementation of our methodology. And I see check is going. Let me go to the recommendation. Okay, we should have, like the National Disaster Management Center should come up with a standard way of reporting, because our main issue here is nobody is reporting landslide when they occur, unless we go in the field and do it. If we have a system whereby people report to the National Disaster Management Center that report to us, it will be helping us in our work. The other thing, like This is what we are doing so far. We are doing it on our statutory budget, which is quite tiny, and we take one part to do landslide survey. But it will help if we have external funding to speed up the process. And then this is all about like accuracy and then verifying what we have so far. So a comprehensive questionnaire to local authorities, as I mentioned before, will help speed up that process and then make this system more accurate. Because as it stands, we wouldn't recommend someone to use it just now as it is, because we need ground truthing and then more accuracy into the map. And finally, this is the contact detail. And then there is a report on this, what I present. There is a full report that we loaded into our website. It's not about only landslide and many other things. If you are interested, just give me an email. I will send you the full report as a PDF file. Thank you very much.
Dr. Soleimani, there's room for some questions. Of course, anybody?
Thank you very. Oh. Hello. Thanks very much for the presentation. I was curious if you could say a little bit more about moving from the national scale that you did, and you showed a couple examples for province, and what would be the main changes that happen when you say you've produced something at a province scale?
Yeah, because this was mainly done through a project we've done with the DST, they were more interested into like national scale. They just want to have an idea where is landslide, because this was done for landslide and other geotechnical problem. So the advantage of going to local scale is like, it's more like accurate in terms of like for urban development and then planning purposes. Because for this map, you can zoom in, it's really not that accurate because red will go to the whole zone, and you cannot say the whole zone is not good for landslide. The advantage of going to local level will give you more precision in terms of like locating exactly where those phenomenon occur.
But it requires a lot more data.
Yes, obviously. The more detailed investigation and more field work. Because I think this was at the scale of 1 to 1 million. So we're thinking of going to the scale of 1 to 50,000. You see like the difference, how it go.
Hello, thanks for the presentation. We saw that like most of the points were indeed in the red areas, but there was also a whole bunch of red areas without points. So is it just because in these areas you didn't have adequate reporting? And if not, do you have some kind of explanation about this possible discrepancy? Thank you.
Yeah, as I said, because we use that theory that says, you know, past hold the key to the future. But we do have some area, we just did like, we assume like if condition A and B and C made landslide occur in this area, if you have the same condition in another area, landslide should normally occur. That's why you'll see red in some area where we have no data whatsoever. And in the conclusion, in the recommendation, I said, you should not take this as it is now because there was no ground truthing. So now the next step should be to do the ground truthing in those areas with red without point to verify if actually those areas have maybe some paleo landslide or some sign of landslide occurring. So we need to do paleo. We need to do some ground truthing, obviously. But yeah, I do agree on that. But they're just based on the modeling that tells this area is has a potential of landslide. But we need to verify that.
Hello, konnichiwa. I'm Japanese.
Konnichiwa. Konnichiwa.
Thank you for studying in Japan. Do you have any example in South Africa that the landslide caused the natural, for example, embankment of natural dam, and then the dammed up water. So then when it failed, so the natural dam failed, so they caused unexpected flooding, so downstream. So such cases are reported worldwide.
The one we have is the one I showed is like Millsplit. It's like the tailing dam, actually. It was in the Free State. That's where those 17 people that died. That's the one example I can, because we can say it's a man-induced thing, because it's the results of mining. They pile somewhere for hundreds of years, and then with the raining and water filling up, it fell into the city, and then it just went down the city and then caused a lot of damage. The other one is the one I show is in the Mutali River, but that one didn't kill anyone because it's a very remote area. But that's a paleo. We estimate it happened 10,000 years ago. So according to the calculation and then estimate, that's the other one I can think of. But other than that, there is no actual example I know of. Maybe it exists, maybe. But those are the two only I know of.
Okay, thank you very much.
Thank you.
In view of the time, I'd like to move to the next presentation. That will be given by Mr. Jerome de Graaf. He's a geologist. He has a lot of experience in emergency response in relation to landslides after forest fires. But he's going to talk about another topic today, about providing landslide information for decision making in regional planning. He's an adjunct faculty of the California State University of Fresno. Thanks for traveling 24 hours here. So please go ahead.
Thanks much. So basically I have spent much of my career dealing with the idea of how to take and develop landslide information and get it involved in the actual planning operation, interacting with the decision makers, with the planners. And a lot of the experience that I gained thanks to involvement with the Organization of American States was involved with areas that you have to say have sort of a scarce amount of information available to be able to work with in developing this approach. So basically, these are some of the things I'd like to talk to, and I'm going to really focus on regional development planning. And I think there are a few people who would disagree with the idea that planning is essential for sustainable development. As far as existing, failing to consider landslide risk leaves infrastructure, homes, and livelihoods essentially vulnerable to damage and loss, and whatever progress we have, either personally or as a society in a particular area, is going to be either slowed at worst and possibly even halted as a consequence of that. When we look at existing development, we need to consider landslide risk for existing development to permit planning options to limit or avoid the financial impact. Some of the talks during yesterday morning talked about approaches that might be done for that. Future development, which of course is something we're going to have more and more of just by increased economic activity, population increases in many parts of the world. Planning for that, we want to try and counter the greater vulnerability that's going to be a consequence of that, and I would think our previous speakers talk about the investment of 845 billion rand is a good example of what we want to try and protect by good planning and using landslide information as part of that good planning to make it happen. So really, just from my perspective and the experience that I've had, we have three levels of planning, and just so you'll understand what I mean when I'm talking about regional development planning. Regional is when you're talking about a country, particularly a small country like Jamaica in this particular case, or it might be a province of a much larger country would be dealing with regional development. And it's usually where the planning is involved with broad allocation of land resources or land for particular purposes where we're trying to essentially set out the framework for the subsequent more detailed planning that's going on. From there, we would go to the local, which might be a large municipality, it might be a parish, county, whatever subdivision fits within that, that is going to be where you're going to be looking at particularly zoning, hazard districts, things where you're getting more close to what the actual activities are going to be in much more detail than agricultural or industrial or something like that. And then site specific is the one that a lot of people are familiar with in many areas, because this is where we've long had a significant amount of knowledge in terms of engineering, where we could do analyses of if we cut a hole this big in the slope of such and such a diameter and an angle, we can test the soils, test the rock, and we can come up with analysis of a factor of safety, and we can include designs for stabilization measures and such at that level to limit the chance of being likely to induce a landslide through that particular process. So basically those are the three levels, and I'm going to stick with the countrywide. I'm sort of a broad brush kind of geologist, so that's where I feel most comfortable. So let's look at what we're dealing with when we're talking about regional planning. One of the reasons that it's important is it lets you implement the widest range of options to avoid or limit landslide impacts. If you've got a highly susceptible area, it means you can decide that you're not going to develop it, or you're going to develop it in such a way that the activities are very unlikely to come together with the inherent nature, the geologic factors, the slope factors in a way that'll induce a landslide. Or, another aspect of it, whatever you're doing there is not going to have a great consequence to a landslide in terms of fatalities, economic loss that's involved if you do that. So that's one of the benefits of regional development planning and and taking a good look at what the situation might actually be. In one of the previous talks yesterday, they talked about if you know that you have some potential at an early stage, you have the opportunity to institute insurance and other financial mechanisms that then mean that if you do have a slide, and you have things that are impacted from that slide, you can mitigate the immediate impact of how much cost in terms of repair, loss that you're doing can be ameliorated by having done these financial things beforehand, which after it happens, nobody wants to give you an insurance policy if your house is already moving down the hill. They're more likely to do it afterwards. So basically, these are the things we're trying to get at. And in order to get there, the planners need zonation maps so that they know where these options need to be implemented. And the other thing that I think is sometimes not fully appreciated is zonation maps are a way to communicate landslide hazards to people who we, like many of us in this room, we can talk landslide to each other. But decision makers and planners don't often know how to speak landslide. So you need a communication tool, and these are one of the things that do it. They show that at this particular point, we're interested in showing the spatial distribution of the potential for landslide activity to happen in the future. We're trying to be predictors. I often stick to the term forecasting because I think we have, in the broad area like this, we have more in common with the weatherman than we do with the engineer at this particular level. So it's more of a forecasting than a prediction. So landslide susceptibility maps are where I've been involved, and which I'll give you some examples of, which are a representation of where in the landscape landslides are more or less likely to occur. And it's really sort of one of the building blocks to ultimately get us to being able to make a statement about landslide risk. This is not the end point, this is the starting point for doing this. It is Not really actual landslide hazard, but as I say, the starting point for where it's going to be. And typically at this first stage, what you're trying to do is to get the spatial representation, and then you're going to try and add the frequency, the temporal part of it, as you work toward the risk. And the other part is at that risk, you have to start talking about what is going to be the effect of that temporal probability in that particular area. So places where landslides occur in the past are the most likely places for landslides to occur in the future. Have we heard that already before today? But it is really a touchstone, an underlying principle that makes a lot of sense. So producing a landslide susceptibility map requires a map of inventoried landslides. And I'm going to say that again because it's that important. If you don't have an inventory of landslides, I do not personally think you can make a landslide hazard map of any kind, and certainly not a landslide susceptibility map. So it's crucial. So consequently, much of the work I've done actually in the field has been to make landslide inventory maps as a starting point. Part of that process, as you've seen in the earlier talk, is helping you understand what are the conditioning or the physical factors in the landscape that seem to favor the occurrence of landslides. The dolerite contacts, for example, that were talked about previously, are an example of what you learn in this process of doing your map to help you understand what are the factors you should then use to combine to develop your landslide susceptibility map. And then you take a methodology, and there are a number of them. We've seen 2 already. I'm going to show you a couple more that is going to work with that data in a way that you can have some confidence that your landslide susceptibility map is representing what you think it's representing. So I'm going to give you 2 examples that come from the Caribbean Central American area from our Organization of American States project in that area, where they were essentially trying to develop methodologies to encourage planners at the regional level to incorporate landslide hazard information in that whole process. Actually, it was for multi-hazards. I was just working on the landslide part of that. So basically, we had a team. I've touched something here. What do I? Oh, he's going to do it, and then I won't mess it up even further than I have already. There. Put my hands in my pocket until I need to push the next thing. Thank you. All righty. So basically, as mentioned in the IGNITE presentation, if you were there, incomplete landslide data poses a problem. So here's an example of how it posed a problem for us. We went to Honduras, or a team did, basically in order to try and develop a landslide susceptibility map as an example to use with the planning community for how to go about doing this kind of work. And they understood that there was basic data like a landslide, or a geologic map available. There were terrain models, so you could develop slope models. And so they were going in to make the landslide inventory model map and then look at those conditioning factors and produce the landslide susceptibility map. But basically, they ended up having missing data. They were doing a province, something appropriate for regional development planning as an example, in the province of Atlantida. So then basically they got there, and it's a good location for doing this. We can see in the foreground that we certainly have a landslide or two. We've got a lot of steep terrain. This was a good site to be doing this. Unfortunately, the bedrock map turned out not to be complete. So consequently, they ended up with a nice inventory map, but they couldn't go any further because one of the basic data that was going to be important as a conditioning factor was bedrock, and it was not complete for the whole area, so you couldn't make a map. So they wanted to leave something that would be at least helpful. So one of the things that we did that you can do when you just have a complete landslide inventory map and you're really short on your other data completeness is to essentially convert it from a bunch of points by a procedure that has been written up in a number of different places to make them into isoplex, or essentially a contoured form that shows the intensity of the amount of area per unit area that has been done. Now, it's not my intention to essentially train you all in how to do this in this particular thing, but essentially you lay a grid over your map, you have a unit area, you have a counter in that, and you just go from over all these overlapping circles until every one of those intersections has a percentage of the area represented, and then you contour it. So this provides at least a interim measure, something that could then say, if you're in the area of the 30%, you've got a much higher potential for a future landslide there than you do over here in this 10%. And honestly, I've worked with people who've said, well, I like your landslide map, and I see that there's 2 landslides here. Can I put the road here between it? Does that mean it's stable? Because there's not a landslide there. And so this is a way of getting around having to make explanations for why that really wasn't a wonderful idea on their part. Now, we did in other examples in this project, we were able to produce our landslide susceptibility map basically by doing a methodology that I had been involved with earlier called matrix assessment. And essentially what you're doing is you're looking at the amount of area of existing landslides in your inventory, the amount of it that's been involved with the combination of bedrock and slope, how much of that of the total landslides that you've mapped are involved with one combination versus another, and then you look at how much of the area that you're studying has that particular combination. You develop a proportion of that area, so you're normalizing the data. You don't want the fact that your area has a huge amount of that bedrock slope combination to sort of override everything else in its importance. And then you use a k-means cluster analysis to essentially develop what are the combinations that essentially define your low to high susceptibility. And then you just turn your map back around by saying every place where I find these combinations that are associated with extreme or high or moderate, where are they? And everything that I didn't find a landslide associated with is low at this particular point. So when I went to Dominica, which I was interested to see yesterday in a presentation, has in the GAR report, has the highest modeled risk of fatalities per inhabitants per year, which is part of why it was chosen for doing some mapping. You can see that for the orange and red, and then the moderate, that pretty much takes up most of the country, and that is the reality given the steepness of that terrain and the way it tends to respond. The extreme is limited to just a couple of spots, and I would also note that the largest landslide that the country had, right there in that orange area, the Matu landslide dam occurred at that particular location a number of years. Let's see, it'd probably be almost 10 years later after this map was created. Now, speaking of that, basically we're interested, as was pointed out earlier, in how good a forecast this is of what we're going to have in the future. You can do it in sort of 2 different ways. When you're making your map, you can choose to take a portion of your mapped inventories, set those aside, and then use those as a way of looking at how well do they fit with what you've modeled with the other landslides. And that's a good way to check your model. But if you want to know how well it's going to forecast, the way you have to do it is once you have your model, your landslide susceptibility map made, you then need to collect slides that happen for some period of time, something that might be representative of the kind of activity that's happened in the past, and then compare how well did it do for those ones that happened subsequent to your inventory. So you have two different options. In Dominica, we took the second option. About 4 years later, we collected all the landslides that had happened during that 4-year period. We'd had plenty of tropical storms and a couple of hurricanes. So we had a good data set from all of that. And that was used to validate the map. And we were very happy to find that indeed it seemed it had the statistics, and I'm not going to drag you into that particular thing here, that showed that we had something we could have some confidence in. So basically, I would advocate that anybody doing this kind of mapping needs to do that kind of validation mapping through either of these mechanisms, through the part of your model to validate your model, and or as a post-inventory slides to validate the forecasting. Now, basically, geologists, as you can see, I would agree, I think, that we're always striving for a more accurate representation of landslide hazard information. That's why we have all of the many different methods that you'll see if you start going through the literature and looking how people have made landslide susceptibility maps alone, much less landslide hazard, landslide risk. You'll see a large number of different approaches, statistical and empirical methods that have been done, and it's natural. That's what we do as scientists, trying to better understand that particular process and develop it. I think in many cases sometimes it frustrates the heck out of decision makers and planners because they are just interested in a good answer. They're not really necessarily interested in optimal scientific accuracy. And as one statistician once said to me, he's a fellow I think very highly of, he said, planners need to know what is the truth as opposed to the God absolute truth. They just need to know the truth well enough to make the good decision that needs to come from that action. There's actually a term developed by Herbert Simon, an economist, that's a corruption of satisfying and satisficing. And basically it is good enough to do the job that you need to do. And I think we as scientists need to remember that because we can overwhelm our compatriots that we're working with in planning with our science to the point where they have a hard time understanding it. And if they don't understand it, are they going to trust it? Are they going to think that it really does what it is? Only if they have confidence in you on a personal basis almost. And we can't necessarily move that generationally into the future. So we need to have a good way to deal with that. So planners need that information so they can make the right decision. So in summary, I'd say for planning, we need landslide susceptibility maps as the minimum kind of hazard zonation. It obviously would be better if we had a temporal component to it as well, and if we had true hazard. Those landslide susceptibility maps need to be reliable enough to support good planning decisions. They need to be understandable to the decision makers, planners, and other stakeholders, not just to us as technical specialists. They need to be able to do that as well. It has to be seen as a tool for communicating landslide hazards. We have to see that as one of its purposes, as well as they need to see it as something they can use as a tool as planners to explain that as well. And then it needs to be important, if you're doing landslide susceptibility mapping, to realize it's a starting point for developing landslide hazard and risk zoning. It's not where you stop, it's where you begin to work it into the process and to develop it and build on that in the future. And that other planning levels are likely to require other methodologies. They're still going to be maybe coming up with the same kinds of end products, but for other situations, it may be more appropriate to use other methods than what you used at the broad level that you're working for planning. Thank you very much. Just for fun, I had to include the Mattu landslide dam right here, so it does plug very effectively, or did up until last July when it failed after 17 years.
Thank you very much. There's room for one or two questions.
Actually, going back to what you just said about how planners need certain kind of information, would it be possible for you to share an example where you were able to actually influence a planning decision, or what actually went into discussing scientific information with planners so that a good planning decision was taken?
Well, other than the fact that I've already met somebody who's told me that she keeps running across my name as they're doing their planning on that particular country's stuff from my previous mapping, there wasn't enough follow-up for me to know some specific ways in which that has happened. In my past other job in the U.S. Forest Service, I work with the planners all the time in doing this sort of thing, and that's typically how it works into, I do the same thing on a national forest that I did in the Caribbean, developing landslide susceptibility maps, and as we planned timber sales and such, then it works into that particular thing. Also, there's an article or a paper that was published in January of this year in Natural Hazards and Earth Science Systems that I'm the author on, that talks specifically to the planning and gives a couple of examples of using it in that particular way. And that's Creative Commons, so anybody can link and get that. And I'll be glad to give you the citation if you want.
Okay. Last question.
Jerome, you may like to know that Donette from St. Lucia is here.
That's who it is.
Annie from Dominica is also in the room. They are using your maps.
That's great. Thank you.
Okay. Thank you very much, Jerome. We move to the third presentation, which is by Professor Malcolm Anderson. His wide experience in slope stability analysis. He's now visiting professor of hydrology, the University of Oxford, and professor of hydrology in the University of Bristol. And his talk will be on community-based landslide risk reduction, evidences, and challenges.
Thank you. Good morning, everybody. Thank you for sort of anticipating this presentation, but I'm also aware you're anticipating coffee, so I'll be fairly quick. We're talking here about really landslide hazard reduction, and that's quite a big step from what we've heard so far this morning, but it's highly linked. It's moving from susceptibility to actually stopping the hazard. Sorry, I'm guilty of the same thing. Just want to quickly have a journey through four aspects, looking at emerging risks, the science base of what we do, the community base of what we do, and the evidence base for the results that we obtain. We're very familiar with graphs and slides of this form showing the scope of the problem that we're faced with, the landslide risk that is present and increasing. And there are four common assertions, I guess, that we have equal familiarity with. One is that risk mitigation pays. But does it actually do that? When you look around, and a number of commentators are increasingly pointing out, there are not that many detailed cost-benefit analyses to justify that assertion. The second assertion is that economic losses due to risk are increasing. Unquestionably, that is true. But what happens when you normalise the data is that there's actually no trend at all. I'll speak to this a little more. The third assertion is that providing the public with information on natural hazards encourages participation. Recent commentaries suggest that's an unfounded assumption. Actually, what you need to do is to engage in self-efficacy. In other words, make people feel confident that they themselves can contribute. That's quite different from giving people information. And the fourth assertion is that the future is going to look pretty much like it is today, but with slight modifications. And if you undertake scenario modelling, actually that suggests quite otherwise. There could be big shocks in store. Let's just return to the economic loss thing. It's quite an important dynamic. This is a curve from Munich Re, we're all familiar with. Proponents of climate change and others assign themselves to this graph to say, look, what's actually happening. But if you normalise the data, and this is from excellent work done at Macquarie University, a group there, you normalise that data, you standardise it for wealth, you standardise it for inflation over the years, you standardise it for building footprint increases. Actually, there is no trend. So what matters is, as we say there, what you build, where we build, and how we build is really important. And nowhere is that more so than in very vulnerable communities, as we'll see in a moment. This violates all the rules of presentation and PowerPoint. It contains far too much information. But just by way of apology, but I put this together, and the more I got into this, the more I thought, actually, I wanted to present it. It's a framework for emerging risks, just as I see it, just for communities. And the first thing just to focus on is the top left, really. There's a number of things that are pretty obvious that are driving the landslide risk. And the first is, of course, there's lack of regulation, typically in unauthorised communities. There's enormous growth of urban populations. On-the-ground delivery of mitigation is fairly rare. And reductionist modelling causes complications. Reductionist modelling is saying, actually, let's make the models more complicated because that'll enable us to understand a lot more. Actually, not necessarily so, as we'll see. But then if you look at emerging risks, well, actually, I've just put those under three categories here. Scarcity of detailed evidence that mitigation actually works. Pretty obvious, really, as I've said, not much on cost-benefit. Do we really know that's the case? There are challenges to adopting mitigation, actually. Samaritan's dilemma. How do people behave when they're offered something? Political agendas change rapidly, and community resonance must be seen as the solution as well as the cause. So there are challenges to adopting mitigation. If you go along the mitigation route, there are then challenges to how do you actually implement it, because there aren't really standards for that, there aren't really exacting standards for community contracting and so forth, and how do we know how we're doing? How do we monitor implementation? So there's a huge raft of challenges to actually delivering something on the ground that makes the hazard reduce. But that's what we did, and I'll show you what we do. A salutary point is that even when there's lots of money available, you'd think, well, we better do something. Actually, not that much is generally done. UN reports and others make this salutary point that when it comes to practical implementation on the ground, very little is done. And yet the drivers for doing stuff are unrelenting. Somebody yesterday said, how long does it take to get a contract sorted out, delivered? Probably 3 to 5 years and delivered. If you put 5 years on the graphs on the left, which I should have done, actually the speed of change is quite astonishing in terms of the millions of people that are now being subjected to increased vulnerability just through where they're forced to live and the properties in which they themselves have to reside. The drive of urbanisation is equally rapid. So things are changing very, very rapidly. And it's a salutary point, as I say, that actually not that much is being done by way of mitigation according to the reports that are available. The point I made about modelling is well founded. Ken Ruther at Pennsylvania University, the Wharton School there, very eminent econometrician, makes the point that actually you can create policy blight by making the numerical models too complicated. You start getting scenario outcomes, everything's sort of possible, Bayesian uncertainties introduced, and what that does is actually sort of make policymakers a little bit uncertain. So what are you really telling me I need to do now? And that's quite an important point, I think. Just finally on this global risk, there's really need for an ex-ante approach. Not enough is being done. It needs to be done now, and it needs to be ex-ante before something happens. So with that as background, we formulated a program which we call Mosaic, which is Management of Slope Stability in Communities. It's seeking to reduce hazard in the most vulnerable communities, and it's seeking to actually deliver on-the-ground mitigation and therefore hazard reduction. And there's a few things here that I suppose kind of make it unique when you add it all together, we think anyway. It uses existing in-country skills, and that's really critical. There's a huge amount of knowledge in the most vulnerable communities, but also within governments, within country. That needs to be tackled. What data do you need? Who's going to be involved? How's it done? Huge raft of decisions just on that line alone. The second thing is it identifies hazard drivers to justify the interventions, and that's really critical. Community residents are engaged throughout the process. We deliver hazard reduction on the ground. Site supervision for that hazard reduction is absolutely critical to ensure the quality of what's delivered. We seek to encourage behavioural change, and we provide an evidence base for the hazard reduction that's undertaken. All of those things require different data streams, as you can imagine. They require a significant number of decisions to be made to enable all those components to be put together and identified properly. So that's really the starting point. The science base that we use, as I say, obviously if you're seeking to reduce risk, you can do three things. You can reduce the exposure, reduce the hazard, or reduce the vulnerability. We are reducing the hazard. The hazard doesn't take much by way of an introduction to see what actually is normally going on. The bottom left diagram or picture is quite interesting in a sense, because what that shows is that people expend what money they do have to think what they can do is improving the situation. As we'll see in a moment, actually it can make it worse. So people are faced locally with choices that are very hard. How do I spend money, if I have the money, to improve the position that I have to reduce the hazard myself? And to do this, and to do it properly, what we need to look at very carefully in these very dense communities is exactly where the water is going, because what we're concerned with here is reducing the trigger, which is rainfall-induced landslide risk. And dense communities, there's a lot of water moving around. People make changes that are very subtle in terms of the dynamics. They might think it's not doing much, but if everybody adopts a similar practice, it adds up to quite a significant change in the risk profile, and therefore the hazard reduction equation set. People can also, as you know, build a house. I was in Jamaica last week and went there it was in Tuesday, went into one community, and Thursday there were another 2 houses built between those 2 days. So density can change very rapidly, and people adapt as they need to. Now, as I say, people do what they do what they can do, and if you build a retaining wall, as that girl was intimating that image, you might think that's affording some protection, but what the animation that we've done analytically on the left shows that with a rainstorm, the water infiltrates the soil, obviously, but it rises, the groundwater then rises from upslope, and actually the retaining wall acts more like a dam, and you can see the hard blue, or the darker the blue, then the higher the pore pressures. And so you can begin to explain why these retaining walls overturn. You walk through these communities, what you see is overturned retaining walls. That's why. But you might think, well, it's not so bad because these communities generally are supplied with mains water, either authorised or unauthorised. a lot of water can be supplied. If you do a basic calculation, the image on the right shows 70% housing density, each one of those properties supplied with water. In that location, that was equivalent to doubling the annual rainfall because there is no drainage. So the simply supplying mains water with an average, and those are metered supplies, is actually doubling the rainfall into a community that's already on a vulnerable slope, but with the absence of drainage provision. So actually, you can see that if we were able to capture and manage the surface water properly, you can staggeringly reduce the number of days per year, number of days per month that the soil is saturated. You can begin to make huge inroads into reducing the risk. But good intentions can actually be manifestly quite dangerous, and the supply of water to slopes is just one of those, quite obviously. So what we try to do is try and capture all this information in detail with the help of the community throughout, point I'll stress later. So we construct sort of models that enable us to place houses on slopes, have point sources of water, know where the drains actually are that are existing but are maybe unlined. And importantly, as the sort of shoebox central diagram shows, we are able to move the water downslope in a way that allows it to either converge at the base, which obviously the pore pressures downslope will be higher, or conversely diverge, should I say, sorry, where the water then moves and dissipates as it moves downslope. Subtle variations in topography at the 50-metre scale or less make huge differences in terms of the triggering mechanisms for landslides. Those have to be known, otherwise you can't reduce the hazard. So knowing what the trigger is, in our case the supply of water, is critical. And actually knowing the scale at which that triggering process is operating is fundamental if you are to reduce the landslide hazard. So that's what we do. And we have some fairly friendly software which some of the residents use because we share the science, and it's with our goal is, which we pleasingly achieve, is that they then explain the science back to us. It's not us just saying this is what's happening. It's a sort of action into knowledge and knowledge into action process that we run and put a lot of store on that. And that really is the science base. The community base is fundamental though. And we start with the community. Remember, they know best. They know where the water goes. They know the experiences they've had. They know the details. We don't know those. So we organise meetings usually around a car that's quite, or a burnt out car. That's usually quite a good focal point to start with. We share experiences, and the lock on is having a plan or a map where people can recognise their own house, and that then unleashes lots of interesting stories and connections about water and their neighbours and everything. So you have to moderate the stories, but eventually you triangulate a lot of information. And this is really important because they realise from the onset that they're the architects behind what we're about to do. They then, with us a little bit, but mostly unaided, they then go around really mapping the slope features. And by this I mean the detailed topography. Where are the points of convergence of water on the slope? Where have there been previous landslides? Where remains saturated all the time? Where are the drains? Where do people discharge their grey water to, etc., etc.? So a lot of detail goes into this, and you end up, or you start with a map that's like top right that people can begin to see what we're trying to do. An important thing here is, of course, that the whole community has to share in this, because you'll end up with drains being built next to somebody's house but not next to somebody else's. And people have to know, as it were, it is for the greater good, as it were, that not everybody's going to get everything that's next to their house, but they understand why. So that's important. Hence the community discussions. And people here are looking at where planned drainage, they discuss these things, they modify them a bit, etc. You end up eventually with a detailed plan. Everybody's house is marked. This is quite a big task, actually, in terms of getting actual houses marked where the drains should go and where existing drains are, because The intervisibility on steep slopes in often densely vegetated slopes nonetheless, but with high density, is not easy. So the GPS methodologies, of course, come into their own with that. These plans are then discussed with local and government engineers and everybody. So good local practice is incorporated. If people have ideas, say, well, I always construct drains like this is how we do it, that's fine, that's incorporated. If they see elements of capacity that they know historically won't work, that's included. And then community contractors, and by that we mean people in the community build the drains. And this is where safeguards are really important, the World Bank safeguards and others, because clearly you go very close to properties, you do all sorts of things that are changing, and we put a lot of effort into making sure that throughout the process people are very cognizant of what's happening and or what will happen, so there are no surprises. What you don't want is somebody to say, well, actually that piece of land you just built on is actually owned by somebody else and I was going to build a room on it anyway, and you're into a whole bag of tricks of problems before you start. So actually doing construction is a very demanding process for safeguards and all sorts of things, so it's pleasing the World Bank has standards. So you end up with features such as this, where actually on about a 50-degree slope, big landslides below, you start building drains that you do calculations for that capture the water, that reduce the landslide hazard. Now, what we're doing here is we're starting in the bottom left. You'll be aware that this morning we were higher up on this diagonal, really looking at country scale, and then Jerry took us down a notch to terrain types and looking at susceptibility mapping. We're right at the bottom left-hand corner here, saying actually if you're reducing the hazard, that is the scale that you've got to be at. It's the hillside drainage area scale. And what you can see therefore is that if you have top-down susceptibility mapping GIS, they'll take you so far, but the question is, and in the discussion it might be an interesting thing to talk about, is really how can we interconnect these scales so that actually if you're about reducing landslide hazard, what's the best capture to help us do that can come down from GIS and other capabilities that are at slightly higher scales, remembering that you've got to, in our case, be at the scale of the triggering process. So what's the evidence base? Governments have money to invest, the bank has money to invest, the World Bank, other people do, so they want answers to two simple questions: does it work and does it pay? Well, evidence that it works really is really critical, and what we've done is we've kept a chronology, of which this is simply an abstraction, the table on the right, a whole bunch of communities, going down here, and the start sort of conditions for these are described, and here there's a major slide resulting in evacuation of 200 homes in an immediately adjoining sector of the hillside on which we were worked. And then, of course, working over the last 5 years on these things, a number of events passed by. Hurricane Dean 2007, the Caribbean 1 in 5 year 24-hour event. But more significantly, about a 1 in 500 year 24 event, Hurricane Tomas in 2010 in St. Lucia, where actually, pleasingly, for the sites that we worked at, there were no reported sides. So having the evidence that things work is really important. And the question is, does it pay? We also, at the beginning, you recall, said there's very few cost-benefit analyses that are really done on detailed projects, and you can see why, because you have to, the questionnaire we developed on the left, that's just one part of it. You have to obviously get direct, indirect benefits really costed, put into dollar values, and it's quite a big process to work out the benefit. You have to then to model the stability, say what would have happened if we hadn't have had the intervention, etc., etc. So actually doing a full cost benefit is quite demanding. The studies we've done, this is published, it's published last year in Natural Hazards, has a cost benefit ratio of 2.7 to 1. interesting, a lot of what I'm saying maps very closely with Andrew Mascary's point of those of you at the GAR presentation yesterday, where of course he made the very correct point that planning controls and things have the highest cost-benefit ratio or benefit-cost ratio. Mitigation, if you don't have the planning, you're forced to do mitigation in a way it's bound to be lower. But at least we need to get evidence as to what it is, and our projects run at that level. Oops, sorry, I've done the same thing. Oh, see, almost coffee time. Next steps. The world is not the same. It's going to change. And undertaking scenario modelling, I can't emphasise this enough. And I think we need to do it. We all need to do it. I think rather more than we are doing. And there was a landmark paper in a journal this year actually on this very point for environmental hazards and so forth. Very serious point, I think. And if you want to say, well, what does this mean? For us, it would mean, I think, developing scenarios, which we're going to do of this form, to say, well, let's assume business as usual. So no real change in poverty in the community we're dealing with, no real change in the regulation, the planning regulation there. They don't abide by it if there is. No climate change and no population growth. Let's do an analysis, let's reduce the hazard. That's what I've described, that's what we've done. But you can say, well, let's assume the poverty in that community gets so much worse. In other words, that might affect that the housing density increases, people subdivide even more water on the slope. There's a trajectory there that worsens the risk and certainly worsens the hazard and would demand a different intervention. Similarly, population growth, similarly, let's make the rainstorms maybe same rainfall but much more intense. Again, change the scenario. And so when you're developing hazard reduction and mitigation, seriously we need to engage in a much more dynamic, much more holistic, much more aggressive scenario modelling, I would suggest. Because we need to then put that on top of, in the regional context, the relevance of the regional level and develop a mechanism for delivery. Otherwise, we're going to be outpaced by the growths of the urban population growth and the growth in people living in the most vulnerable conditions, those two slides that I showed you from the GAR report at the beginning of the talk. Coffee time, more or less. This whole methodology from start right through to implementation has been written up, and the book is being published by the bank, World Bank, out in September of this year. It'll be free to download on the web. And so thank you for attending, and I thank both the World Bank and the Latin America Caribbean group for funding much of what we've been speaking about today, and GFDR as well. So, but also thank you for your attention.
Thank you very much, Malcolm. We are indeed running 10 minutes already into coffee time. But if there are questions, then happy to extend that a little bit.
Okay, thank you. Thank you very much for the very enlightening presentation. Although your presentation was focusing on urban landslide risk reduction, my interest would have been to know how we can apply this to reduce landslide risk reduction in the rural context. Yeah. And when talking about the community-based approach, it's very exciting. But one thing I wanted to find out from your perspective, which possibly I did not hear, is about the use of early warning systems. Can we use early warning system at the community level to with landslides? So that's my concern. The rural nature of landslides and the intervention that can be undertaken, and then the early warning component.
Yeah, sure. Yeah, I can be very brief. Rural, yes. we've been asked to. We were asked to do that. It's just that pressure of time, I think, meant that we were in demand to do urban communities. But we did a pilot, a very brief pilot for rural communities, and this was where actually that there was basically rotation of agricultural practice on very steep slopes. So you can begin, as you can appreciate, I think, saying, well, what will the stability analysis look like if you build a sort of irrigation drains and you start draining the soil with a particular agricultural practice? So the answer, yes, you can adopt the sort of general philosophy for rural applications. Early warning, yes and no. A colleague of mine in Indonesia, Rita Kanawaski from the university in Yogyakarta, has done a lot on early warning work for landslides, and that's quite impressive in terms of community. They have simple things linked up to the soil water pore pressures that alerts communities, and it's active. It's funded by UNESCO. It's quite an impressive. I can give you her contact details after, but rather than directing me commenting, it's far better that you speak directly to her. There's a lot of work there that she's done, which I think is really quite good. But thank you for the questions.
Okay, thank you very much. Yeah, we are quite late, so I had also a wrap-up presentation, but I'll leave that. It also showed some initiatives internationally on how to get more information on methodologies for landslide hazard and risk assessment, and also training opportunities. If you're interested in that, you can contact me directly. I think we are still, compared to other types of hazards, we're in a disadvantaged position, because landslides are very localized phenomena. You cannot generalize things as you do in other studies. Data is really important, and I think that the inventory data, as was also mentioned, is a key thing. And I think one of the major developments in the future should be that we link new developments in open data and also in involvement of many people through internet and through smartphones, or even through these simple phones that we saw in the initial session, to report many more information on landslide events. Only because by having that information we can convert those susceptibility maps that I just say from high to low to something that says this is likely to happen, this many events in this period of time. And that would be really convincing to decision makers, that they could really say, well, if 80% of your map is moderate, then what should you do as a planner? If you can outline at this location there is a 50% chance of having a landslide in the next 5 years, that's another type of information. So we're not yet there, but that makes landslide study so interesting. I thank you very much for your attendance. Thank you for the speakers, and enjoy your coffee break. Thank you.